Welcome to this problem walkthrough. Today, we'll be solving LeetCode problem number 111, titled Minimum Depth of Binary Tree. In this session, we'll explore the problem statement, break it down into manageable steps, and walk through an efficient solution. Let's dive in. In this problem, we are tasked with finding the minimum depth of a binary tree. The minimum depth is defined as the number of nodes along the shortest path from the root node to the nearest leaf node. A leaf node is a node that does not have any children. The input to the problem is the binary tree itself, represented by a reference to its root node. The output should be an integer that represents the minimum depth of the tree. To better understand this, let's look at some examples. In the first example, we have a binary tree with 3 levels. The root node is 3, which has 2 children, 9 and 20. Node 20 further branches out to 15 and 7. The shortest path from the root to a leaf is through node 9, which is at depth 2. Therefore, the minimum depth of this tree is 2. In contrast, the path to nodes 15 or 7 is longer, so they do not determine the minimum depth. In the second example, the tree is skewed to the right, forming a straight line from the root node 2 down to the leaf node 6. Here, the only path to a leaf involves traversing all 5 nodes, starting from 2 and ending at 6. As a result, the minimum depth of this tree is 5. This demonstrates how the structure of the tree impacts the minimum depth calculation. In the third example, the tree has 3 levels, with the root node 1 branching out to nodes 2 and 3. Node 2 further branches out to node 4, but the shortest path to a leaf is through node 3, which is at depth 2. Therefore, the minimum depth of this tree is 2. When solving this problem, keep in mind the constraints, such as the tree containing up to 100,000 nodes, and edge cases like empty trees, skewed trees, or trees with only a single node. For instance, if the tree is empty, the minimum depth is 0, while a single node tree has a minimum depth of 1. To determine the minimum depth of a binary tree, one natural approach is to use depth-first search, or DFS. This method leverages recursion to explore each branch of the tree until it reaches a leaf node, which is defined as a node with no left or right children. Along the way, we track the minimum depth encountered. To implement this, we start with a base case. If the root of the tree is null, we return a depth of 0, as an empty tree has no depth. If we encounter a leaf node, we return a depth of 1 since we've reached the endpoint of that path. For nodes with only one child, we calculate the depth of the non-null subtree to avoid mistakenly considering a non-leaf path is shorter. Finally, for nodes with both children, we calculate the minimum of the left and right subtree depths and add 1 to account for the current node. While this approach is simple and straightforward, it has trade-offs. It visits each node exactly once, resulting in a time complexity of O(n), but the recursive call stack can grow to the height of the tree, making the space complexity O(h). This could lead to stack overflow for very deep or skewed trees, which is worth considering when deciding on this approach. Another effective method for solving this problem is the breadth-first search, or BFS, approach. Unlike DFS, which explores depth first, BFS traverses the tree level by level. This makes it ideal for finding the shortest path, as the first leaf node encountered during the traversal will always be at the minimum depth. To implement this, we use a queue to facilitate level order traversal. We start by enqueuing the root node with an initial depth of 1. As we process each node, we check if it's a leaf node. If it is, we immediately return its depth, ensuring we stop as soon as we find the shortest path. For non-leaf nodes, we enqueue their non-null children with an increment depth. This approach ensures every node is visited exactly once, maintaining a time complexity of O(n). However, the space complexity depends on the number of nodes at the widest level of the tree, which can be O(n) in the worst case for a full binary tree. While BFS guarantees finding the minimum depth without unnecessary exploration, the use of a queue does require additional memory, which is a trade-off compared to DFS. A third approach involves optimizing the standard DFS method by introducing pruning. The idea here is to avoid exploring branches once it's clear they cannot yield a shorter depth than one already found. To achieve this, we maintain a global variable to store the current minimum depth. As we traverse the tree using DFS, we pass along the current depth. If this depth exceeds the global minimum, we stop further recursion down that branch, effectively skipping unnecessary work. Whenever we reach a leaf node, we update the global minimum if the path is shorter. This optimization makes the algorithm more efficient in cases where pruning can significantly reduce the number of nodes visited. The time complexity remains O(n) in the worst case, as every node may still need to be visited, but in the best case, pruning can save substantial computation. The space complexity is O(h), as it still relies on the recursive call stack. While this approach can be more efficient than standard DFS, it is slightly more complex to implement and requires careful handling of the global variable to ensure correctness. Among the approaches considered, BFS stands out as the preferred strategy for solving this problem. This is because BFS aligns naturally with the task of finding the shortest path. By processing nodes level by level, it guarantees that the first leaf node encountered is at the minimum depth, allowing us to avoid exploring deeper or unnecessary branches. Additionally, BFS does not suffer from the risk of stack overflow that can occur with recursive DFS, making it more robust for handling trees with significant depth. While it does require extra memory for the queue, this trade-off is often acceptable given its clarity and reliability. Compared to optimized DFS with pruning, BFS is simpler to implement and avoids the need for additional logic to manage a global minimum or early termination conditions. Overall, the straightforward nature of BFS and its alignment with the problem's requirements make it the most suitable choice for finding the minimum depth of a binary tree. The key insight that reinforced the choice of BFS was the realization that it inherently finds the shortest path by design. This was the turning point in deciding on the approach, as it ensured that the problem could be solved efficiently without unnecessary complexity. Another important observation was that a leaf node is encountered only once during a BFS traversal, and this guarees the correctness of the solution while avoiding redundant computations. These factors combine to make BFS not only the most intuitive but also the most optimal strategy for solving the problem of finding the minimum depth of a binary tree. The problem of finding the minimum depth of a binary tree requires us to determine the shortest path from the root node to the nearest leaf node. A leaf node is any node that does not have children, meaning both its left and right pointers are null. To solve this, we can use a depth-first search, or DFS, approach. The intuition behind DFS in this context is to explore each branch of the tree recursively until we reach a leaf node, keeping track of the minimum depth encountered along the way. The algorithm begins by defining a base case. If the root node is null, the tree is empty, and the depth is 0. If the root itself is a leaf, we return 1, as it represents the minimum depth. From there, we proceed with recursive traversal, focusing on handling cases where the root has only one child or both children. Let's dive deeper into these steps next. If the root node has only one child, we recursively calculate the minimum depth of the subtree where the child is not null. This ensures we only consider valid paths that lead to leaf nodes. For cases where the root has both left and right children, we calculate the minimum depth of each subtree separately. Once we have both results, we return the smaller of the two values, adding 1 to account for the current root level. Finally, after exploring all possible paths in the tree, the minimum depth is returned as the result. To make this clearer, let's walk through an example. Consider a binary tree where the root node is labeled as 1, with 2 children, 2 and 3. Node 2 itself has 2 children, 4 and 5, while node 3 is a leaf node. We'll now see how the algorithm processes this input. Starting with the root node, labeled as 1, we see that it has both left and right children. First, we traverse the left subtree, which begins at node 2. Node 2 has 2 children, nodes 4 and 5, both of which are leaf nodes. Since they are leaves, their depths are each 1. Adding 1 for the root level of node 2, the minimum depth for this subtree becomes 2. Next, we examine the right subtree, which consists of node 3. Because node 3 is a leaf, its depth is simply 1. Comparing the depths of the left and right subtrees, we find that the smaller value is 1, from the right subtree. Adding 1 to account for the root level of node 1, the overall minimum depth of the tree is 2. This example illustrates how the DFS approach efficiently calculates the result by focusing on the shortest path to a leaf node. Now, let's highlight some key insights from this approach. First, DFS is well suited for this problem because it allows us to explore each branch of the tree thoroughly and evaluate its depth. Since our goal is to find the minimum depth, it's essential to examine all possible paths. Second, handling edge cases is critical. For instance, if the root is null, the depth is 0. Similarly, if only one child exists at any node, the algorithm correctly ignores the null child, ensuring that invalid paths are excluded from the calculation. For balanced trees, both subtrees are explored equally, while for unbalanced trees, special attention is given to missing branches to ensure correctness. Finally, the recursion is optimized to stop once a leaf node is encountered, which avoids unnecessary exploration and improves efficiency. The binary tree structure and the recursive stack are central to implementing this solution effectively. The recursive stack plays a crucial role in maintaining the state for each branch during traversal. At any given point, the stack holds the current node and its depth, allowing the algorithm to backtrack and continue exploring other branches as needed. In terms of complexity, the time complexity of this approach is O(n), where n represents the number of nodes in the tree. This is because each node is visited exactly once in the worst case. For space complexity, the maximum depth of the recursive stack is proportional to the height of the tree, denoted as h. For a balanced tree, this height is approximately log n, while for a skewed tree, it can reach n. This balance between time and space efficiency makes the DFS approach a robust solution for finding the minimum depth of a binary tree. To solve the problem of finding the minimum depth of a binary tree, we start by importing the deque class from Python's collections module, as it will help us implement a breadth-first search or BFS. Next, we define a tree node class to represent each node in the binary tree. Each node has a value and pointers to its left and right children. After that, we create a solution class, which contains the minDepth method to calculate the minimum depth. Inside the method, the first thing we do is check if the root is null. If it is, we return 0 because an empty tree has a depth of 0. Now, to perform the BFS, we initialize a queue using deque. Each element in the queue is a tuple containing a node and its corresponding depth. We start by adding the root node to the queue with an initial depth of 1. Then, we enter a while loop that continues as long as the queue is not empty. Inside the loop, we dequeue the first element, which gives us the current node and its depth. At this point, we check if the current node is a leaf, meaning it has no left or right children. If it is a leaf, we immediately return its depth, as this is the minimum depth of the tree. If the current node is not a leaf, we proceed to add its children to the queue. For every left child that exists, we append it to the queue along with an increment depth value, indicating we are moving one level deeper in the tree. Similarly, if the node has a right child, we append it to the queue in the same way, also with an increment depth. This ensures that the BFS continues level by level, exploring all nodes at the current depth before moving to the next. Using this approach, as soon as we encounter the first leaf node, we return its depth, guaranteeing the minimum depth of the binary tree is found efficiently. Here, we begin with the definition of a binary tree node. The tree node class represents each node in the tree, storing an integer value along with references to its left and right child nodes. This class has two constructors, one for initializing just the value, and another for initializing the value along with its left and right children. Next, we define the solution class, which contains the method minDepth. This method calculates the minimum depth of the binary tree, starting with a base case. If the root node is null, meaning the tree is empty, we simply return 0. To solve this problem, we're using a breadth-first search approach, which is implemented using a queue. Here, we create a queue to hold pairs of nodes and their corresponding depths. We then add the root node to the queue, paired with an initial depth of 1. Using a while loop, we process each node in the queue until it's empty. For each iteration, we retrieve the current node and its depth by polling the queue. The first thing we check is whether the current node is a leaf node, that is, it has no left or right child. If it's a leaf, we've found the minimum depth, so we return the depth immediately. Otherwise, we add the node's children to the queue, each with a depth increment by 1. This ensures that we explore all nodes level by level, and as soon as we encounter the first leaf node, we return its depth. This efficient approach guarantees that we find the minimum depth without unnecessary traversal. Finally, we define the pair class, which is a helper class used to store a key-value pair. In our case, the key represents a tree node, and the value represents the depth of that node. The pair class includes a constructor to initialize the key and value, along with methods to retrieve each of them. This design ensures that we can easily associate each node in the tree with its corresponding depth as we process the queue. By encapsulating this logic in a simple class, we maintain clean and organized code. With this implementation, we've completed our solution to find the minimum depth of a binary tree using a breadth-first search approach in Java. To solve the problem, we use a breadth-first search approach to find the minimum depth of the binary tree. In example 1, we start with the given tree structure. The root node, which has a value of 1, is added to the queue along with its depth, initialized as 1. The queue now contains the tuple 1, 1. In the first step, we dequeue this tuple, meaning we are processing node 1 at depth 1. Since node 1 is not a leaf node, it has children, we enqueue its left child, node 2, and its right child, node 3, each with a depth of 2. The queue now contains 2, 2, and 3, 2. Next, we dequeue the tuple 2, 2, which corresponds to processing node 2 at depth 2. Node 2 is also not a leaf since it has children. Therefore, we enqueue its left child, node 4, and its right child, node 5, each with a depth of 3. The queue now contains 3, 2, 4, 3, and 5, 3. Finally, we process the tuple 3, 2, which corresponds to node 3 at depth 2. Node 3 is a leaf node because it has no children. As a result, we return its depth, which is 2. This is the minimum depth of the tree. Now let's look at example 2, which involves a single node tree. Here, the tree consists of only the root node with a value of 1. We initialize the queue with this root node and its depth, which is 1. The queue contains the tuple 1, 1. In the first step, we dequeue this tuple, meaning we are processing node 1 at depth 1. Since node 1 is a leaf, it has no children, we immediately return its depth, which is 1. This makes sense because for a tree with only one node, the minimum depth is always 1. Next, consider example 3, where the tree is unbalanced. The root node has a value of 1, and it has two children, node 2 on the left and node 3 on the right. Node 2 further has a left child, node 4, which itself has a left child, node 5. This unbalanced structure requires the same breadth-first search strategy to determine the minimum depth. For the unbalanced tree in example 3, we again start by initializing the queue with the root node, which has a value of 1, and its depth of 1. The queue is now 1, 1. In the first step, we dequeue 1, 1, meaning we are processing node 1 at depth 1. Since node 1 is not a leaf, we enqueue its children, node 2 and node 3, each with a depth of 2. The queue now contains 2, 2, and 3, 2. Next, we process the tuple 2, 2, which corresponds to node 2 at depth 2. Node 2 is not a leaf, so we enqueue its left child, node 4, with a depth of 3. The queue now contains 3, 2, and 4, 3. In the next step, we process the tuple 3, 2, which corresponds to node 3 at depth 2. Since node 3 is a leaf, it has no children, we return its depth, which is 2. This demonstrates that even in an unbalanced tree, the breadth-first search ensures we find the minimum depth efficiently. The time complexity of this algorithm is O(n), where n is the total number of nodes in the binary tree. This is because the algorithm uses a breadth-first search, or BFS, to traverse the tree level by level. During this traversal, each node is visited exactly once, which contributes to the O(n) complexity. Additionally, for each node, we perform a constant amount of work to enqueue its children, such as the left and right nodes, and later dequeue them for processing. Since these queue operations are performed for each node just once, they also scale linearly with the size of the tree. When combined, the traversal and queue operations both lead to an overall time complexity of O(n). The space complexity of this algorithm depends on the maximum number of nodes present in the queue at any given time, which is determined by the tree's maximum width. In a perfectly balanced binary tree, the widest level can have up to approximately n/2 nodes, where n is the total number of nodes in the tree. In this case, the space complexity for the queue would be O(n). On the other hand, in a skewed binary tree, where all nodes are on one side, the queue will hold at most one node at a time, resulting in a space complexity of O(1). Additionally, the algorithm uses a constant amount of auxiliary space for variables like depth and pointers, which adds O(1), but is negligible in the overall calculation. Therefore, the space complexity is O, W, where W represents the maximum width of the tree. In the worst case, this can be O, N, while in the best case, it can be O, 1. In the best case scenario, the root node itself is a leaf node, meaning the algorithm immediately finds the minimum depth and returns a value of 1. Here, both the time and space complexities are O, 1. In the average case, the tree has varying depths, and the BFS ensures that the minimum depth is found efficiently, typically visiting fewer nodes than in the worst case. However, the time complexity remains O, N, in terms of the asymptotic upper bound. In the worst case, the tree is balanced, and the BFS must explore all levels of the tree before encountering a leaf node. This results in a time complexity of O, N, and a space complexity of O, N, as the queue would store nodes from the widest level. Compared to a naive depth-first search or DFS approach, BFS is more efficient. While DFS can have a time complexity of O, N, in the best case, it can degrade to O, N squared in unbalanced trees, as it may explore all paths unnecessarily. Furthermore, DFS has a space complexity of O, H, where H is the height of the tree, due to the recursion stack. With the BFS approach, the time complexity is consistently O, N, because every node is processed exactly once, and the queue operations for each node take constant time. The space complexity is O, W, where W is the maximum width of the tree, as the queue size is proportional to the number of nodes at the widest level. In the case of a balanced tree, this can be up to n/2 nodes. The mathematical justification for these complexities lies in how BFS finds the minimum depth. By stopping as soon as the first leaf node is encountered, the algorithm avoids unnecessary traversal of deeper levels, ensuring optimal performance. This makes BFS both time and space efficient for solving the minimum depth problem of a binary tree. It outperforms naive DFS not only in practical efficiency but also in providing strong asymptotic guarantees. One of the most common mistakes when solving this problem is confusing the minimum depth with the maximum depth. Remember, the minimum depth is the shortest path to a leaf node, not the longest. Another frequent issue is not handling null children correctly. For example, if a node has one null child and one non-null child, you should only consider the depth of the non-null child. Assigning a depth of 0 to the null child can lead to incorrect results. Let's say a node has a right child with a depth of 3 and no left child. The correct minimum depth for this node would be 4, not 1. Next, inefficient DFS implementations can also cause problems. Without pruning unnecessary branches, especially in larger trees, you may end up with excessive computation. It's important to stop the traversal as soon as you encounter a leaf node. Finally, don't overlook edge cases like an empty tree, which should return 0, or a single node tree, which should return 1. Addressing these scenarios ensures your solution is robust and complete. Another common error occurs when using BFS but failing to stop at the first leaf node. BFS is particularly suited for minimum depth problems because it explores level by level, so once a leaf is found, you don't need to process deeper levels. In interviews, these types of problems often test your understanding of tree traversal techniques, whether recursive or iterative, and your ability to optimize with early stopping. Although both DFS and BFS can solve the problem, BFS is typically the better choice here due to its natural fit for finding the shortest path. Always be prepared to discuss edge cases with your interviewer. For example, confirm how an empty tree or a single node tree should be handled, and be ready to address unbalanced trees where nodes might all be on one side. Also, clarify what qualifies as a leaf node. This is usually defined as a node with no children. This problem shares similarities with other tree-based challenges, such as finding the maximum depth of a binary tree, checking for a specific path sum, or calculating the sum of root-to-leaf numbers. Understanding these related problems can deepen your grasp of tree traversal patterns. When it comes to approaches, the DFS method is straightforward to implement recursively, but it can be inefficient since it might explore unnecessary branches. While the time complexity is O, N, the space complexity depends on the tree's height, reaching O, H, in the worst case. On the other hand, the BFS approach is often more efficient for minimum depth problems. It stops searching as soon as the first leaf is found, reducing unnecessary computations. The time complexity is still O, N, but the space complexity depends on the width of the tree, or O, W. Lastly, an iterative DFS using a stack gives you greater control over the traversal process. However, it can be more complex to implement and debug compared to the other methods. Another approach to solving this problem is divide and conquer. Here, you break the tree into smaller subproblems by solving for the left and right subtrees separately. This method is intuitive and works well for many tree-related problems, as it mirrors the recursive structure of trees. However, for finding the minimum depth specifically, divide and conquer may not be as efficient as BFS, since it doesn't inherently prioritize the shortest path to a leaf. While it can still achieve a correct result, it often involves more computation than necessary. So, while this approach is worth understanding and discussing, BFS remains the optimal choice for this particular problem due to its efficiency in finding the shortest path. Great work! To recap, we solved the minimum depth of binary tree problem using the DFS approach. We discussed its time and space complexities, key takeaways, and how this knowledge can be applied to other tree problems. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!